Okay, so we'll now look at the actual structure and components of a GLM. And the setup we're looking at is the one we've looked at so far. So we observe a response data y1 through to yn, along with a k by 1 vector of explanatory variables for each unit I. Now we want to specify the GLM as a regression model, and our objective is to estimate the effects of the x variables on the conditional mean response, just as we have done in lectures 4, 5 and 6. Now in the linear model, the conditional mean is modelled via a regression function, and that's what we're going to do here. So as in the case of the linear model, the conditional mean is going to be modelled by a regression function depending on an unknown set of parameters, an unknown k by 1 parameter vector. We'll make the assumption throughout that the response data are independent, with some distribution belonging to what's called the exponential family of distributions, and I'll explain in a minute what that means. Now the key point for now that I'm going to go through is the GLM has three components that I need you to understand. It's got a random component, a systematic component, and a link function. And I'm going to want to define each component in turn. So, the random component of a GLM specifies a particular probability distribution, e.g. a density or mass function, for the response variable yi with expected value μi. As I said, typically this is a distribution in the exponential family. We'll talk about that in a minute. So notice that unlike the linear model, when we talk about the random part, we're not talking about an error term. We're defining the random part directly in terms of the distribution of the response variable. So that's the first component of a GLM, the random component. Second, we have the systematic component, and this should look quite familiar. The systematic component relates a function of the mean of yi, g of μi, to the covariates, and it does so in the form of eta equals x transpose I beta. So this is really exactly a linear and parameter structure that we've already met in the context of the linear model, and we call this linear form the linear predictor in the context of GLMs. But notice that unlike the linear model, we have a function of the mean relating the mean of the response to the predictor. In the linear model, the mean is related directly to the predictor, so the function is the identity function. For other GLMs, it will not be identity. There could be a nonlinear function. And the third component of a GLM is called the link function. That's the function that I've just mentioned. The link function relates the systematic component to the expected value of the response. So it describes how the mean of μi relates to the linear predictor. It has some important properties. It's monotonic, which matters because we need to be able to invert it. And it's twice differentiable, which matters when we come to maximize the likelihood function, because we're going to use differentiation, of course, to find those optimal values. Now there's a thing called the inverse link that simply goes in the other direction. Applying G inverse to the linear predictor gets us back to the mean. But this is important. This function here is what's going to allow us to take a linear predictor and project it, if you like, onto a distribution that's non-normal. It's going to give us a function that gets us from a linear predictor of the covariates back to something like a binary random variable or a count random variable or whatever non-normal response we're looking at. So with these key three components, what you can see is that GLM somewhat relax the strict linearity assumption of linear models by allowing the expected value of the response to depend on a smooth, monotonic function of the linear predictor. But because GLMs are specified in terms of the linear predictor, many of the general ideas and concepts of linear modeling carry over with little modification. Basic model formulation is much the same, but with the following exceptions. First, a distribution and a link function must be chosen, two of the three components that I've just described. Second, the variance is now allowed to be a function of the mean response. So as the problem we talked about in section 6 is dealt with automatically. Lecture 6. Third, coefficients must be interpreted via the link function, They can't be read as in the simple linear model way, as the examples later will make clear. Fourth, model fitting has to be done iteratively. There's no closed form solution in general for GLMs. And fifth, the distributional results for inference are approximate. They're justified asymptotically rather than giving exact finite sample results. So I now want to look in more detail at two of the components of a GLM before turning to estimation. First, I want to talk about exponential family distributions and explain what that means. And then I'm going to talk about link functions. Okay, so the exponential family. We're going to restrict our discussion of GLMs to those that belong to the exponential family. An exponential family is an important concept in statistics and very important for GLM estimation because it makes matters much simpler. Now, the exponential family simply comprises the set of probability distributions that can be written in a certain algebraic form. It can look complicated, but it's really as simple as that, and its properties align almost perfectly with the structure and assumptions of GLMs for 5 reasons. So the exponential family aligns very nicely for 5 reasons. First, it provides a unified framework. Exponential family distributions share a common mathematical form, and that commonality allows a unified treatment of various response types, continuous binary count, and so on, all within the same basic GLM framework. Second, the canonical parameter, the log likelihood of an exponential family distribution, is linear in what's called the canonical parameter, which leads to a straightforward computation of derivatives and makes maximum likelihood estimation computationally simple. I'll discuss the canonical parameter in a minute. Third, we have link functions. The structure of the exponential family lends itself naturally to the concept of a link function, and many commonly used links correspond naturally to exponential family distributions. Fourthly, computational simplicity. Data for exponential family distributions can be reduced via so-called sufficient statistics without losing information relative to parameter estimation. And fifth, the variance function in exponential family distributions. The variance is allowed to be a function of the mean. This variance, this relationship captured by the variance function, is exactly what allows the model to handle different forms of non-constant variance. So collectively, these features mean that exponential family distributions are highly adaptable and computationally convenient for the GLM framework. But what is the exponential family? So let me define it. Here's the definition. A PDF or a PDF of random variable yi depending on a natural or canonical parameter, theta I, is a member of the exponential family if the density can be written in this form shown in the slide. That is the exponential of yi theta minus this function of theta, b of theta I, divided by a of phi, plus c, function c of yi and phi. That is for known functions a, b, and c, where phi is called the dispersion parameter. So we need our densities, our probability distributions, to be able to be written in that form. And as we'll see in a minute, many of the most common probability distributions can be written in that form. Now let me walk through the components. Theta is the canonical parameter. This is what will eventually relate to the linear predictor. Simple as that. The function b is really important. It plays the central role in determining both the mean and variance of the distribution itself. The function a, involving the dispersion parameter phi, is relevant to the variance, and c is essentially an arbitrary function of y and phi that just tidies things up. It takes different forms for different distributions. Now, let's return to this function of the canonical parameter beta phi, because this is important. The moments of an exponential family distribution are related to the derivatives of that function b. The expected value of yi is the first derivative of b with respect to theta, and the variance of yi is the second derivative of b times a of phi. That's how we work out the variance. The second derivative of b is called the variance function, written v of mu I, and it determines how the variance of y depends on the mean of y. So first derivative of b gives the mean, second derivative gives the variance function, and the dispersion parameter along with the mean determine the variance. Often a of phi is just phi times some weight. So as I said, many common distributions can be written in exponential family form, and the table shows how that can be done. It breaks down all the components for the normal, the Poisson distribution, the binomial, the gamma, and the inverse Gaussian. Now reading across the rows, the first row gives the notation and the range of the response, then the canonical parameter for theta. For the normal, it's simply mu, as you can see here. For the Poisson, it's log mu. For binomial, it's the log of mu over n minus mu. The dispersion parameter phi is sigma squared for the normal distribution. It's 1 for both the Poisson and the binomial. And then we have the function b of theta. For the normal, that's theta squared over 2. So if we put these together, and one thing I want you to do in your own time is write these in this form. Do it for the normal distribution. Well, actually, I'll show you that in a second anyway. I've done it anyway. But let's check the machinery with the normal, since that's the distribution at this point that we know best. The first derivative of theta squared over 2, the first derivative of this function here is theta, which for the normal we know equals mu, so that gives us an expectation of mu. So the first derivative of b gives the mean of mu exactly as it should. The variance function in the bottom row is the second derivative of beta squared. That for the normal is equal to 1, and that tells us that the variance is unrelated to the mean. So that would be the variance function times phi, which would give us sigma squared. So in exponential family form, what we've shown is the normal has mean mu and variance sigma squared. For all the distributions it differs. So for the Poisson, for instance, the variance function is mu. That is, the variance is actually equal to the mean. For the binomial, it's mu times 1 minus mu. So you can see here in this table how the idea that the exponential family allows the variance to be a function of the mean plays out across different distributions. So that's the exponential family. I now want to talk about the link function. The link function is a monotonic differentiable function that typically maps the parameter space for the mean onto the real line. It makes explicit the nature of the relationship between the linear predictor and the mean, g of mu I equals eta I equals x transpose xi beta. So it has that form there. Now each member of the exponential family has a canonical link function, which equates the natural parameter with the link function directly. That's the definition on the slide. So a canonical link occurs when g satisfies g of mu I equals theta I. The link transforms the mean directly to the natural parameter of an exponential family distribution. And for a GLM, use of a canonical link means that theta I equals the linear predictor itself. That's what it means. So very, very simple. Now canonical links can permit computational simplifications. For example, the model will have a concave log likelihood function and simple form sufficient statistics and likelihood equations, and some canonical link functions are shown on the next slide. So let's just go through this table. For the normal distribution, the canonical link is the identity. The mean is directly related to the linear predictor, exactly the same as we saw in the linear model in previous lectures, and that's how the Gaussian distribution appears in a GLM. It's just going to have an identity link. I kind of mentioned that at the start of the lecture. From the Poisson model, the canonical link is the log, so we're going to relate the log of the mean to the linear predictor in the Poisson case, and going in the other direction, the inverse link tells us that the mean of the Poisson is the exponential of the linear predictor, since the exponential is the inverse, of course, of the log. For the binomial, the canonical link is logit, the log of mu over 1 minus mu, related to the linear predictor. The inverse link is the logistic function, shown here, 1 over 1 plus e to the minus x transpose beta. The table also shows the gamma and the inverse Gaussian links, the negative inverse and the inverse squared, though we won't cover these in the lecture. So I realise that all of this material can seem quite abstract on first encounter. Actually, if you work through these definitions, plug things into the distribution that we've got shown here, you'll find it's very, very simple. But to make matters concrete, I now want to derive the GLM components for three common distributions, all with canonical link: the normal, the binomial, and the Poisson. Let's start with the normal. So suppose y is a normally distributed random variable with mean mu and variance sigma squared. The random component of the GLM is then just the usual normal density, which is shown at the top here. With a bit of algebra, we can rewrite this density in exponential family form as shown, and I'd encourage you to go back to the definition slide and verify that it can be written in that form yourself, just to make sure you're happy with it. The mapping is theta equals mu, phi equals sigma squared, a of phi equals phi, b of theta equals theta squared over 2, and c of y and phi is the expression in brackets shown there. This one here. So applying the rules, the mean is the first derivative of b, function b, which is theta, which equals mu. That's as expected. The variance is a of phi times the second derivative of b, which gives phi. Phi is equal to sigma squared. Again, that's correct because that gives us the variance of the normal distribution, and it's unrelated to the mean. And the canonical link in this case is identity, giving g of mu I equals mu I itself equals x transpose I beta. So the mean response is related directly to the linear predictor and is exactly the systematic part of the usual multiple linear regression model. So a GLM with a Gaussian response and identity link is just a linear model, but we're going to still treat it as a GLM, and later on we'll estimate it using maximum likelihood estimation. Okay, next the binomial. Suppose ny is a binomial distributed random variable, so y here is the sample proportion of successes with expected value mu equal to pi, the success probability. The random component is the binomial mass function shown at the top, which you met in lecture 1. Again, we rewrite this density in exponential family form, and I encourage you to verify the algebra as usual. The mapping is as follows. Theta equals the log of pi over 1 minus pi. The function a of phi equals 1 over n. The function b of theta equals the log of 1 plus e to the theta. And the function c is the log of the binomial coefficient. The dispersion parameter can be taken as 1. So applying the rules once more, the mean is the first derivative of function b, which works out as e to the theta over 1 plus e to the theta. And the variance is a of phi times the second derivative of function b, which after calculus and algebra gives pi times 1 minus pi over n, the familiar binomial variance. And again, a function of the mean. The canonical link for the binomial leads to the specification of a logistic regression model, which is perhaps one of the most widely used GLMs that we have for binomial data. There are other choices actually. We could use a probit model, but the logistic model relates the log of pi I over 1 minus pi I directly to the linear predictor. The left-hand side is called the log's odd, and it's modelled as linear in xi, so changing variable xj by 1 unit changes the log's odds by beta j, and we'll look later at how to interpret that in practice. Okay, and the third and final example I want to give is the Poisson distribution. So suppose y is a Poisson distributed random variable with mean mu greater than 0. Remember, the Poisson is the distribution for a non-negative integer count, and it only has one parameter because the variance is equal to the mean, the so-called equidispersion assumption. The random component in this model is the density shown here, the Poisson density, or the Poisson mass function, and it can be rewritten in exponential family form in that form shown there. So again, reading off the components, theta equals the log of mu, the function a of phi is equal to 1, the function b of theta equals e to the theta, and the function c of y and phi is minus log y factorial. The dispersion parameter in this distribution is taken at 1. So again, applying the rules, the mean is the first derivative of the function b, which is e to the theta, and the variance is the second derivative of b, which is also e to the theta. So the mean equals the variance exactly as we expect for an equidispersed Poisson random variable. The log link is the canonical link and is the standard link function for Poisson regression. It generates the familiar log linear model. The log of mu I is equal to beta transpose xi, the log of the Poisson rate related to the linear predictor. In this model, changing xj by 1 unit is associated with a change in the expected response by a factor of e to the beta j. And again, we'll see how that plays out in interpretation when we get to the applications later in this lecture, when we actually estimate some GLMs. But okay, so in this section, what I've tried to do is I've tried to explain the components of a GLM. I've focused on what the exponential family distribution looks like, and we've gone through some concrete examples to show how we can write some standard density in exponential family form and then pick off the variance and the mean by applying some calculus to the exponential family form distribution.